Okay, hello, welcome. I hope you're here for digital design and computer architecture. Who's excited about the topic? Okay, great, I see a lot of hands. Hopefully all hands will be up there. I see two hands of some people, so we can double count. Okay, so this is going to be a fun semester, hopefully, because it's a fascinating topic. And my role in this particular lecture will be to motivate you about the topic. So we're going to cover some interesting things that are happening in computer architecture today, really today, like in 2019 and 2020. And I'll show you some recent examples from what's happening. And then we're going to talk about some basics of computer architecture. So it's going to be a fun lecture, hopefully. So feel free to ask questions also in the meantime. One thing I will say, in all my lectures, going toward the latter part of the semester, it's better if you actually follow me and what I say, as opposed to try to read everything that's written on the slides. Because there may be some cases where slides have a lot of things so that you can study later on. But when I lecture, it's really a lecture. It's not really the slide themselves. So if you actually start reading everything on the slide, you may get lost and you may actually lose the momentum of the lecture and what I say. So keep that in mind, please. That's really important. Okay? Because my bandwidth sometimes tends to be faster in terms of slides per minute or slides per second. Okay? Okay, and you can always slow me down by asking a question. Keep that in mind. If you have a good question, yes, there you go. You're exercising that.
First, hopefully, important question, will this lecture be recorded?
So yes, all of these lectures will be recorded. They will be on both ETH servers as well as on YouTube. You can actually see older incarnations of this particular lecture, starting from 2017 all the way to 2019 on YouTube, as well as on ETH servers. So attendance in the lectures is really not mandatory in the end, but hopefully you'll have fun if you attend the lectures and you'll learn more through this interaction. But you can always go back to YouTube and the ETH servers to actually see what we've covered. Okay, and actually all of the materials of this course are online, except for the solutions to the labs. Any other questions? Okay, then we can start. So let me first introduce myself. Well, this is not working. So the first important thing in designing a computing system is to make it work. So we're going to focus on that in this lecture, basically. If this thing doesn't work, I'm not going to be able to use it clearly, right? So functionality is the first and most important thing. Okay, so let me introduce myself. I'm a professor here in the informatics department, as well as ETH. I've been here since September 2015, and the first time I taught this course was 2017, and this is the fourth time we're teaching it, and every iteration we're improving it. And I think the first time I taught it, there were 280 students, and now you're 500 or so. So clearly, the size of the student body and interest in computer science is growing. And I should also say that the interest in computer architecture is growing in the world, as we will see. Before coming here, I was a professor at Carnegie Mellon University in Pittsburgh, and you're going to see some examples of that, or remnants of that. I still have some PhD students over there. I got my PhD doctoral degree from University of Texas at Austin. I got my bachelor's degrees from University of Michigan. And after I got my PhD, I started the computer architecture group at Microsoft Research, which is interesting, right? You would think of Microsoft as a software company. What do they have to do with hardware? But you will see that all companies are going into hardware today because you really need to get the highest efficiency and highest performance of the workloads that you're trying to execute. But yeah, I started the computer architecture group over there, so we did a lot of interesting research, some of which you will see. And then I moved to Carnegie Mellon because I really wanted to teach and do academic research. But I continuously worked with companies. I worked at Intel and AMD on cutting-edge microprocessor designs, and later at Google and VMware on both hardware and software designs. And I still work a lot with companies to see what kind of future designs can be useful for different companies of the world. Okay, so you can reach me with my email. There's an ETH email also, but it doesn't always work. So I prefer something that works more often. That's why I put my Gmail over there. But you can send it to ETH email and test your chances. And if you don't get a response, you feel free to send it again, because there's a lot of redundancy. And email is a really bad communication medium these days, especially since the volume of email is growing. And you can find my website. If you search for my name, you can find it over there. So I do research and teaching in especially computer architecture, computer systems, computer security, hardware security, and bioinformatics. You'll see a lot of these topics pop up today as well as during the course of this semester. But yeah, you can see we do a lot of work on memory and storage systems, hardware security, safety, predictability, fault tolerance, hardware-software cooperation. How do these things work together to make better systems? And architectures for bioinformatics, health, medicine, and machine learning and artificial intelligence. So there's a lot of interesting topics. And this is one very busy slide that is an example of what you should not be reading, and you should just be following me when you come to this sort of slide. Basically, these are some things that we're working on, and we're going to actually see a lot of this in this lecture, in this course. We're going to actually start with the basics, of course, of all of these components, the transistor itself, and then we're going to build up a small microprocessor. How does that microprocessor operate, which is actually inside this, and inside this, and inside this also. And then we're going to see different types of processing, like graphics processing, for example, or systolic arrays, which we will see. Those are similar to those are paradigms that people use to accelerate machine learning, for example, today, but they're more general than machine learning as well. And we're going to see memory as well. We're going to see different types of memory when we get to it. So you'll actually get exposed to a good chunk of the system around here. And always keep in mind that we're going to, of course, cover the basics and fundamentals and principles, but we're going to also look at what's happening at the cutting edge in the field today. Because we do cutting edge research in the field, spanning applications, systems, and logic, with architecture, computer architecture at the center. So it's really important to see how fundamentals actually relate to the cutting edge today. And you will see some of that today and tomorrow. Okay, so I didn't cover any of this, but you can read them on your own if you're interested. Okay, so these are some key directions that we're following in research, and I will talk about this so that you have some idea of what is going on in the field today, but we're going to cover them a little bit more tomorrow. So today, it's very interesting that people are trying to design much more fundamentally secure, reliable, and safe architectures. We've had a lot of security, reliability, and safety problems recently, especially as the technology scales down to smaller nodes, meaning that as you make the transistors smaller and smaller, you get into a lot of reliability issues and security issues, and safety is clearly important. And as we design workloads that we rely on, as we design computing systems that we rely on more and more in our lives, like self-driving cars, this becomes a lot more important, right? Because you don't want your self-driving car to be unsafe. You don't want it to be unreliable. You don't want a simple bit flip. Maybe you store some number and a bit in that number flips, so it becomes wrong. You don't want that to cause you an accident, right? So this is very fundamental to especially the important workloads that we're going to use into the future. And that's happening. So this is very, very important for that reason. And we will see examples of this. That's why it's really important to also know the fundamentals of how computers work, because these bit flips are actually happening today, as I will show you in a little bit. The second one, of course, energy efficiency is extremely important. We all want things to be much more efficient. And sustainability is actually even more important today. We're having a huge climate problem, as you probably know. We're having a huge sustainability problem going into the future. And computing devices are actually consuming a good chunk of the power that we actually generate in the world. Actually, there were some studies. Maybe I'll bring it up later on, but if you actually want to train a very large machine learning model that, let's say, Google uses in their data centers, I believe some of those machine learning models take 30 days or longer to train on hundreds of computers. So you're basically tying up hundreds of computers for 30 days or longer just to train a machine learning model so that that machine learning model can predict what you're going to buy next. So does that sound like a sustainable solution to you? I'm not sure. So keep that in mind. Clearly, technology enables these things. They could be used for good or bad. But if the technology, you cannot maybe prevent all of the bad uses or all of the useless uses, let's say. But you can make the technology much more efficient such that those useless uses will not become non-sustainable going into the future. So we're going to talk about that. Energy efficiency is a big problem today. And we're actually going to talk about memory-centric and data-centric architectures. But keep in mind, we're going to start with the basics. So we'll get back to that. Low latency and predictable architecture is really important. Actually, I have a very recent example from this. Low latency is good because you basically get to the answer very quickly. For example, if you're doing genome sequencing. Today, actually, it's really important to the genome sequencing. I'll give you an example in a little bit. You're probably living in the age of coronavirus, right? Everybody heard of coronavirus? Okay, good. And people are not even raising their hands because it's not serious, maybe, right? Yeah, basically, it is serious. But if you can actually analyze the RNA or the DNA of this virus very, very quickly at low latency, then you can actually get to a treatment much faster. And I'm going to give you an example of that later on, very brief, not too long. That's why designing these low latency of processing engines is becoming a lot more important. You may always question, why do we want faster computers? And that question has always been asked, actually. In the 1980s, I'm going to give you an example when we get to the lecture, when we talk about pipelining. In the 1980s, people were designing a processor called MIPS R2000. And they said, oh, that's a beautiful design. And it's very high performance. Why do we need anything faster than that? And now, we're in 2020, we've built a lot faster computers, and we still want faster computers, because there will always be applications that will benefit from it. And this coronavirus is a really good example, in my opinion. Predictability is a little bit different, actually. Low latency is good, but predictable means you really want your system to be predictable. Let me give you an example of the difference between low latency and predictable. So I was trying to catch this tram that was supposed to arrive at 12:20 yesterday. Now the tram arrives at 12:23. It's late, it's not predictable, so I may miss the next tram, right? So that's not good. If the train arrives at 12:19, that's also not good. That comes earlier, because I may actually miss it, because I'm banking on the fact that the tram is arriving at 12:20, right? And actually that happened. I came to Bellevue Platz at 12:20, actually at 12:19, I believe, when the tram was supposed to still be there, and the tram was gone. So I had to walk from Bellevue Platz all the way to the main building for my meeting. Actually, I had to run, because I was about to miss my meeting. And I did actually become late because of that. So this is an example of a predictable system. If you're a predictable system, you have a deadline, and you actually meet the deadline. You don't get earlier than the deadline, you don't get later than the deadline. You just meet it at the right time. And there may be applications of this that are really important. I mean, this, of course, caused me some trouble. I had to run, right? But there could be other applications that are actually have problems. For example, if you launch a space shuttle and it has to meet some target in space, you have to reach that target at the right time to take the picture at the right time, right? And this has happened, actually. People actually send Voyager or other types of space shuttles. If you actually are too early at the target, you miss your opportunity to take the picture that you're supposed to take, right? And that's an example of a predictable system where you really need that predictability guarantee. And you're spending billions and billions, well, millions and millions, maybe. I don't know actually the cost, but it's a very large cost to build this shuttle and send it over there and make sure that it works and it meets the target at that point in time, right? Okay, so that's another example. We will talk about that a little bit, keep this in mind, but we're not going to actually go into a lot of detail on how to build really predictable architectures. And actually, today's architectures are not very predictable. The general purpose architectures that you have today are not very predictable. There's a lot that goes into predictability. It's a very difficult design problem in the end. If you end up building these shuttles that go into the space, you will see that that's not easy. Okay, and then the last direction is over here is the architectures for artificial intelligence, machine learning, genomics, medicine, and health. Basically, important applications, I should say, over here. But these are some of the important applications that I listed. And these are actually these are actually directions that people are following, and my group is also following, to actually make things much more efficient and much faster. And I'll give you some examples of these in a little bit. Okay, any questions so far? Okay, so that was my introduction a little bit. So what will we learn in this course? I think, simply put, we're going to learn how computers work from the ground up. I assume you know programming, right? How many people know programming? Okay, that's good. Everybody should, because you've taken a course. How many people know how computers work? Okay, some people really know. That's good. That's good. Somewhat, yeah. How many people think they know how computers work because they know programming? Okay, that's good. Because programming is not, being able to program doesn't mean that you know how things work underneath, right? You have an interface and somebody executes those programs. And in the end, to know how computers work, you need to know how those programs get executed. In this course, we're going to take a bottom-up approach and start from the basic building ground, which is really the transistor itself. And we're going to assume that that transistor works, although we'll see that there are difficulties in making that transistor work today also. But assuming that that transistor works, you can actually build up a computer that can execute programs. And that's the function of this course. Of course, we will also talk about why we care. Hopefully that's becoming clear as I talk about these directions, right? We care because we want to solve problems. Well, I guess I scooped myself. So why do we have computers? Anybody? Or why do we do computing? To solve problems. And we have a lot of problems as humanity in the end. And we create problems also. And that's good because we actually create good problems as well as bad problems. And we want to solve all of them in the end, right? So I don't think we're going to be out of problems at any time soon. Some of them are, let me tell you what I mean by good problems. Good problems are problems that exist in nature. For example, we want to understand the nature so that we can actually have a better quality of life. Bad problems are problems that are caused by us, like congestion, climate problems, and who knows, pollution, right? We still want to solve bad problems also, right, that are caused by us. Okay, so another rewording of that answer. In order to solve problems, you need to gain insight into the problems, and computing actually helps with that insight. Computing may not be able to solve all of those problems directly, but it can actually enable you to get insight into the problem so that you can solve that problem in some way. Of course, the premise of artificial intelligence is that the computer itself can solve those problems for you, right? But that's not an easy goal, and we're clearly not there at this point. And actually, if you want to know more about this insight, how many people here know about Richard Hamming or Dick Hamming? Okay, how do you know about him? Exactly, yes. Hamming codes, error correcting codes. He's actually he developed the early theory for enabling error correcting codes, Hamming codes. We'll talk about Hamming distance maybe at some point. But I would recommend this book that he wrote, Numerical Methods for Scientists and Engineers. And here he talks about the purpose of computing is to gain insight. And you will see that in a later slide also. Okay, if you extend the answer, basically, we want to gain insight. We want to solve problems so that we can enable a better life and future. I'm not going to belabor that. As I said earlier, there's always a bigger need for more efficient and faster computers. But we're going to talk about how does a computer actually solve the problems. And my answer to this, in at least the dominant technologies that we use today, is by orchestrating electrons. At the very bottom of the layer, you have electrons, which are governed by the laws of physics. And you basically orchestrate those electrons, make sure that they move to the right place, and create voltage differentials so that you can actually solve the higher level problems. That sounds good, right? How many of you can talk to an electron today? Can you speak the electron language? Well, before that, have you ever taken a physics class? Yes, of course, right? You probably took a physics class, you know what an electron is. But you cannot directly talk to an electron, right? Hopefully not. Well, if you talk to an electron, let me know. But we have actually created layers of transformation so that we can actually enable electrons to do what we want them to do. Basically, the question is how do we actually solve the problems using electrons? And that leads us to the transformation hierarchy. At the top, we have a problem. At the bottom, we have electrons. Clearly, we don't speak the language of electrons, so we cannot tell the electron, solve this problem for me. So what we do is we convert the problem into an algorithm, and then convert that algorithm into a program written in some language, and execute that program using some system software, and compile it down to some hardware-software interface, instructions that could be understood by the hardware, and that will be implemented by what's called the microarchitecture, which is the hardware itself. We're going to define these more clearly as we go along. And that will be implemented by the logic gates, and that will be in turn implemented by the devices, like transistors, which in turn operate based on the laws of physics, which are really electrons in the end. And this is the transformation hierarchy, basically. We go through this transformation hierarchy in computing. And if you think about what a computer is, it's really the entire thing, of course, but computer architecture has traditionally been defined as this part, the interface to the hardware, interface between the software and the hardware, and the microarchitecture, basically how it's implemented. In this course, we're going to take a broader view, and I'm going to give you the reason why we're taking a broader view, because we want to actually get higher performance and higher efficiency. And if you want to get higher performance and higher efficiency, you cannot just restrict yourself to understanding this part. You really need to understand a lot of things across this. So even though the focus of this course will a lot of the focus of this course will be logic, microarchitecture, hardware, software interface, we're going to touch upon some of these also. But keep in mind that today's computer architectures have a much more expanded view. And I'm going to give you some examples of that. Some of them, for example, take some algorithms and implement them in very specialized hardware so that they can actually accelerate those algorithms much faster. Neural networks, for example, are an example of those algorithms, and they're implemented with a very specialized hardware. So you actually design the entire system to accelerate that neural network. And these things exist, and we will see some examples of that. Okay, so let's go a little bit more into this levels of transformation. And this is decamming, if you haven't seen him before, this with his cat. And in the end, the purpose of computing is to gain insight, and we gain and generate insight by solving problems. And this transformation hierarchy exists to solve the problems. And let's go into this. So basically, we need to express the problem in terms of an algorithm. You've taken an algorithms course, correct? Yes. So you know what an algorithm is. I'm not going to spend a lot of time over here. But basically, an algorithm is a step-by-step procedure that is guaranteed to terminate, where each step is precisely defined and is executable by a computer. Executable, meaning basically it has three characteristics. It needs to be finite. It needs to complete. It needs to be definite. It needs to be precise enough to be executed. It needs to be effectively computable, meaning that a Turing machine should be able to complete it. Now, you may not understand what a Turing machine is right now, but an analogy from human is, so you can actually think of a human as a computer also, right? And if I want you to do something, let's say you go from this point to some other point, and if one of the steps says you have to jump over a building, that's not effectively computable for a human computer, right? As a human, unless you're a superhuman. So basically, these steps need to be there. And many algorithms can exist for the same problem. And they all need to have these properties, but they may have different efficiencies. Okay. So again, this is not an algorithms course, but it's always good to know what an algorithm is in the end, because they're the things that are going to be executed on the system. Okay, once you have an algorithm, you translate it to basically write a program that implements the algorithm in some language, and there are many languages. How many people know Java here? Okay, that's good. How many people know C? Okay, fewer. How many people know Python? Okay, more. What about Scratch? Okay. Okay, we could go. We could basically take a poll of these clearly, and clearly not all of you know all of the programming languages, but the basics are in the end the same. Okay, so you compile the program into. You convert the algorithm. You write the algorithm in a program, and then that program gets executed. We're not going to talk about all aspects of the runtime system here, but and you will see that later on when we take operating systems. And it's really important to take that course. But the program itself eventually gets compiled to instructions. And this is the hardware-software interface. This is called the ISA. And we're going to talk about that a lot after we introduce the basic digital logic part of this course. So ISA is the instruction set architecture. It's really the interface or contract between the hardware and the software. It's what the programmer assumes that the hardware will satisfy. So you basically have an add instruction, and the programmer assumes that the add will work in some way, and the hardware is supposed to satisfy that way. So it's really a contract in the end that's defined by some human. Okay, and that ISA gets implemented underneath using what's called a microarchitecture. And it's really, microarchitecture is really, its definition is an implementation of an ISA. And there could be many implementations of an ISA, as we will see. A given add operation, for example, if you're adding two numbers, there are hundreds or thousands of ways you can add that number using different logic gates, using different ways of connecting transistors. And we will see some of them. We won't see hundreds or thousands of ways, but we will see some of them. And there are hundreds of, these hundreds of ways differ from each other in terms of the trade-offs they make. Some of them are faster, but much more power hungry. Some of them are very slow, but very power efficient. They don't consume a lot of area, for example, on chip. So there are a lot of trade-offs that we will see in microarchitecture. And that's the beauty of what we're going to study, actually. You can make a lot of trade-offs at this layer, as well as at this layer, to design a computer, so that you can actually design a computer that meets the requirements that you actually want to achieve. Okay, underneath the microarchitecture, we'll see the logic gates. So this is the digital logic circuits. Essentially, these are building blocks of the microarchitecture, gates. For example, an AND gate that ANDs two numbers, two bits is a very basic logic gate. A NOT gate, an inverter that takes a bit and inverts it, is another logic gate, right? So we will see that, we will build up. And underneath logic gates, you have devices that consist of essentially transistors. So in this course, we're going to cover this part, especially as I said earlier, but we're going to start with the transistor over here as a building up. And so I gave this top-down approach so that you have a good idea of what happens top-down right now. But the course will follow a more bottom-up approach, as we will see starting from next week. Okay, so then what is computer architecture? So in the broadest definition, I will define computer architecture as a science and art of designing computing platforms, starting from the hardware to the interface and to the system software and maybe the programming model as well. Today, actually, programming models could be part of your computer architecture, especially if you want to specialize and take an algorithm and execute on some specialized hardware. That's why I have this broad definition over here. Traditionally, it's the hardware and the interface. It doesn't even go to the system software sometimes. But it's good to have the broader definition because in the future, you're going to be probably designing systems or working on systems, and you may be actually programming in some languages that are executed on specialized hardware. Okay, so I say science and art, even though this is a computer science class. I don't believe everything we do is science because it's not possible to design a computer for 5 years later completely scientifically. So if you look at building architecture, for example, it's not completely scientific also. There's a lot of art that gets involved in building architecture. In computer architecture, it's very similar. You're designing something for use 5 years later. And that's possible. I've been using this computer 5 years. It's not doing very well right now, but I've been using it for 5 years. I've been using this for 5 years almost. And it's been designed 5 years, not just 5 years ago, it's been designed a few years before 5 years ago. That makes sense, right? Because you design this, and then there's some time to actually make sure it's produced and validated, and then it gets shipped, and I buy it some time later than when it gets shipped at the first time because I don't want to pay my arm and leg to Apple, for example, right? And as a result, this lifespan of this is using components from 8 years ago, let's say. So somebody actually designed this computer 8 years ago, and they have to predict what the users will ask for 8 years later. Right? That's not easy. I do not know of any science at this point that can predict that. That's why part of it is really art. And whenever we make design decisions in computer architecture, whenever we want to design some system, yes, you do as much as science as possible to actually model the system and to understand the boundaries of it and to understand what kind of performance it will get. But it's going to be very difficult for you to get the performance of that system, basically model the performance of that system 8 years from now. Because it depends not only what's happening to the hardware, but also what's happening to the user itself, right? Maybe I want something completely different from what this person designed 8 years ago, right? So keep that in mind. That's why it's very much art as well. So we're going to see a lot of trade-offs, and we're going to analyze them both from a scientific perspective as well as an art perspective. And we're not going to be able to always quantify the best trade-offs because the reason, in the end, the answer is usually will be it depends. It depends on the usage and environment. If the usage is like this, then you may want to make this trade-off. If you use this in some other way, you may want to make some other trade-off. Okay, basically, it's the science and art of designing computing platforms to achieve a set of design goals. So a design goal also comes into the picture. And there may be many different design goals that you may have. For example, some supercomputers are designed with this sort of design goal. You want to get the highest performance on Earth on some specific workloads. Or some actually accelerators are designed this way also, some neural networks, right? You basically customize your design as much as possible in this case, and you only care about highest performance. It's never true, as we will see in a little bit. You always, you usually have a priority of constraints when you're designing, and your goal may be highest performance, but then you have secondary goals as well. And usually cost is a constraint that you have. Okay, or there could be other design goals, right? You want to get the longest battery life at a form factor that fits in your pocket with low cost, or with some cost that's less than some target, right? So now we can get actually more specific in terms of goals, right? Or you want to design a computing platform that gets the best average performance across all known workloads at that time, or all workloads that you really care about at that time, at the best performance/cost ratio. Now you can see that this is actually much more general purpose design, right? Here, maybe you're a very special purpose, especially if you want to accelerate a single application. It's very special purpose. But this is now becoming more general purpose. You want to get the best average performance. Here you can think of an accelerator that accelerates or makes faster a neural network. Neural network is the only application. Here you can think of a general purpose Intel processor or an AMD processor that can execute any workload that you have. Right? So, and computer architecture actually spans all of this space. That's one of the reasons why it's really exciting. It's not just general purpose, it's not just special purpose, it's really across the space. And today people are designing processors, systems that are both special purpose and general purpose. This system, for example, even though it was designed 8 years ago, let's say, it has not only a general purpose processor, but it also has specialized processors like graphics processors. It also has a video encoding, decoding accelerator, and newer versions of this have machine learning accelerators also. So there's a lot that goes on over here. It has some data movement accelerators also, which we're not going to talk about now. Okay, so basically you can keep adding more goals over here. In the end, your design goals dictate the design decisions that you make. Okay, so as I said, designing a supercomputer, which is over here, is very different from designing a smartphone, which is over here. And that's also, in turn, very different from designing a general-purpose computer. And you can keep expanding this. But many fundamental principles are, in the end, similar. And in this course, we're going to start with those fundamental principles. And later, we're going to talk about some of these different accelerators, if you will. And let me give you some examples of these different platforms and different goals. I'm not going to go into detail over here, but you can look at these pictures and think that they actually have different goals, right? Like these have different goals compared to these over here. But they are computers also, or they're, well, not everything over here is a computer, clearly, but they're governed by a computer. You have a different design goal over here, right? If you want to design a self-driving car that is like this, you'd better be very, very careful. I would like to be able to do that, actually. It's not bad, right? But I don't think I will trust the car underneath me at this point. And hopefully the goal is to trust it at some point in time, but it's not clear if we will ever reach that point, right? Okay, so this is actually another self-driving car. I like this picture over here because this shows that people put, at least in this version over here, which is, I don't know, maybe 2010 or so, they have a huge machine over here, huge set of computers to actually do the calculations to make sure that the self-driving car actually goes the right way, right? Of course, that communicates with a lot of sensors that's in different parts of the car also. Okay, and this is a completely different platform, right? You can look at a data center, and that data center is a completely different platform than this one. And the constraints are completely different, as you can see, right? Here, energy efficiency should be a constraint. Here, maybe energy efficiency, less so of a constraint. Power could be a constraint, certainly, if you want to execute a lot of workloads, but energy may be less of a constraint. And this is a supercomputer. This was, I'm not sure if it's still the fastest, but this is Tianhe 2 in China. And that was one of the fastest supercomputers of its time. And the design, even though this and this may look similar, this is really designed for extremely high performance on particular workloads, scientific workloads, whereas this is really designed for high throughput, let's say, on many potential workloads, or maybe some workloads like Gmail, right? If you pick Gmail. Okay, I'm going through these relatively quickly, but just to give you an idea of the variety of platforms that you can enable after you actually take this course and hopefully become experts in it. So this is another example. This was introduced by Google in 2017. This is a board that can accelerate neural networks. And it operates based on very fundamental principles that we will cover in this course later on. It's a systolic array, essentially. It's an array of processing elements where data is pumped into the array, and the processing elements do the computation, and they pump out the data on the side. So it basically is a specialized matrix multiplication unit. It's very interesting, right? Neural networks do a lot of matrix multiplication, and what these folks at Google and many other companies right now actually also found out that if you really want to do these, if you really want to train a machine learning model efficiently, you really need these accelerators. Because existing general purpose computers are not good at doing those matrix multiplications and other things, convolutions that are inside the neural network computations. They are very slow, they're very energy inefficient. So what Google said was, even though they're a software company, they designed this hardware board, including the processing unit and everything around it, to ensure that the neural networks that they execute in their data centers are executed efficiently and fast. And that's exactly the reason why today computer architecture, that's one of the reasons why the computer architecture is very widespread. Because what you would consider traditionally like a software company, right? Google, Microsoft, Facebook, they're all software companies. But they're all doing hardware because they cannot get to the scales that they should get. They cannot execute their workloads efficiently and fast enough without this sort of processing engines. And if you want to take advantage of this sort of processing engine, you then need to write your software so that it can be executed by this processing engine much faster and much more efficiently. So in the end, this is really a system that takes an algorithm and designs a specialized hardware to actually execute that algorithm much faster. I would call this an algorithm hardware co-design, as we will see in a little bit. Okay, so that's one example. This is another example. This was recently introduced, I think last year, by Tesla. And if you're actually interested, you can actually read the papers that I'm pointing out to. There's a YouTube video on this particular one. This is actually the self-driving computer, as they call it. It's essentially another computer that enables Tesla to actually do the self-driving much more efficiently and at much higher performance, because they cannot use general-purpose computers easily because they have many issues, performance, energy efficiency, and reliability. But they actually design their chips to actually execute the algorithms that they need on their self-driving car much faster. And they actually have 2 of these chips. It turns out they both do the same thing. Why? Because they want a reliable engine, and if one fails, they want to detect that fails. So they both do the same thing, and if they disagree in the result, that means that there must be a fault that occurred in the system. This is a very fundamental principle of redundancy. You basically add redundancy into the system so that you can detect the faults in one computing unit. So if some bit flip happens in this particular unit, you get some answer that will not match the answer that's provided by this one, and you can actually detect that something went wrong. Now, if you actually have 3 of these units, which becomes more expensive, clearly, you can vote between them, right? If one of them is wrong, and if the other 2 agree on the answer, then you can say, oh, that's my answer, right? You can do voting. That's called triple modular redundancy. It's an expensive way of tolerating faults, but now you can actually tolerate the fault. Here, if you get disagreements between the 2 processors that are doing exactly the same thing, that means that something is wrong, but you don't know what the right answer is because which one do you trust, right? They're all equal from your perspective. Maybe you can go and do some analysis and figure out later on, but you cannot basically take an answer online while the system is operating. So you have to stop something. But if you have 3 of these, then you can actually do voting. And if you have 5 of these, clearly you can do voting over there, and you can tolerate 2 faults if you have 5 of these. But you can see that there's a trade-off between reliability and cost in this case. If you want to be more reliable, you add more processing elements. Yes, you can tolerate more faults, but the cost of the system also increases. And cost also comes with power, because clearly you're executing 2 things here, but you could be executing 3 things, 5 things, and also energy. Okay, but they made the design choice that this was important for them, so they actually used these 2 units, and they operated them in lockstep, synchronously, to check their answers. Okay, so I will give this axiom to you. Basically, this is what I'm going to assume. To achieve the highest energy efficiency and performance, we really must take this expanded view of computer architecture. Basically, we go from all the way from problems to electrons, and computer architecture really needs to expand between algorithms and devices. And what I've shown you earlier are examples of these algorithm architecture co-designs. So we really need to co-design across the hierarchy, algorithms to devices, and specialize as much as possible, of course, within the design goals that we have. Okay, so this course, keep this in mind. We're going to start very general purpose, because the fundamentals of all of these processing elements are really the transistor in the end. But then we're going to specialize a little bit. Maybe we'll never specialize as much as the state of the art, although we will cover some machine learning accelerators in the systolic arrays lecture. We will cover GPUs, for example. But things are, of course, moving fast today. But keep this in mind. It's not only general purpose. Any questions so far? Am I speaking too fast? No? Yes? Who says yes? Who says no? Okay, I see more no's. Okay, so let me motivate you a little bit more. We're going a little bit slower than I thought, but let's keep going. So today, there are many interesting things that are happening in computer architecture. I'm going to give you an overview of these. I'll start with performance and energy efficiency. And I've given you some examples of it, so we're going to skip some of these quickly. But this is one example. This is something that was introduced in 2019. This is an example from the memory space, where you store your data, for example. And this looks like a regular memory module that you put on your computer, right? And normal memory modules are DRAM, dynamic random access memory, which means that whenever you plug off the power, you lose your data. That's memory, that's not hard disk. But this is a different type of memory that was introduced by Intel in 2019, and you can buy it. You're going to pay a lot for it, but if you're interested, you can buy it. You can put it into your system, and this is non-volatile main memory. It uses 3D X-point technology. You don't need to understand what the technology is, but basically, whenever you plug off the power, your data still stays over here. So it's very similar to your DRAM. It's close to DRAM in terms of speed. It's very fast. But its characteristics in terms of volatility is very similar to your hard disk. So today, hard disks are much slower, but this technology makes access to persistent data or non-volatile data much faster compared to hard disk, similar to what you have in your DRAM. Which sounds fascinating, right? And actually, if you have something like this, then the question becomes, how do you actually redesign your programs to take advantage of it? Because if you think about the systems today, whenever you write a program, you treat memory and files separately, right? Whenever you want to access a file, which is persistent data, you basically open the file somehow and bring the data into memory. Whereas whenever you want to manipulate data structures, you do direct loads and stores, right? In your program, basically, you have an array. And you assume that your array goes away whenever you actually unplug your computer. Which means that if you want to persist something, if you want to have some data, your program persists some data, you have to manipulate files. But this can actually fundamentally change that. You actually can directly manipulate files in your memory. So you can have a persistent array, for example. I'm not going to go into the more detail of this one. You can think about it. Yes?
Would this mean that turning it off and on again would degrade in effectiveness?
What does it mean? Oh, yeah. Basically, if you want to actually get rid of bugs in your system by turning something on and off, yes, they will persist in this case. You're right. So there could be downsides to this also. So any technology has upsides and downsides. There are trade-offs, right? This is a very fast memory that can enable you fast access to persistent data, but data persists, meaning that if you're relying on the fact that you're losing data from your memory whenever you power it off, now you're not getting that anymore. Meaning that if someone gets your memory, then they can actually steal your data, right? That's one example of it. Or you're not starting from a clean slate when you restart your system. Okay. But this is actually very fascinating, I think. There are a lot of disruption that could be caused by it. But this is not easy. Actually, this is based on, Intel doesn't admit it, but if you actually redo the research and look at the papers, this is based on some technology called, in my opinion, phase change memory. Phase change memory is very interesting, actually, because it's used in rewritable CDs. You know rewritable CDs? Has anybody used them? Okay, some people. Maybe you're too young for these things. Because rewritable CDs are also going out of fashion in terms of media. But basically, it's a memory type that can store data in different phases, and it can actually reliably switch between different phases. And recently, people have discovered ways of reliably switching between different phases very, very quickly. Okay. If you're interested, we can actually look at some papers. But this sort of thing, to make it happen, it takes a long time. Because you really need to work on the devices, you really need to work on the technology, you really need to enable this sort of thing to make it reliable. And actually, this is something very close to my heart, because when I joined Microsoft Research, this was something that we were doing research on. And we published this paper in 2009 in the International Symposium on Computer Architecture that essentially talks about this thing, let me say. Basically, can you replace the main memory, DRAM, with a phase change memory? And we actually did a lot of feasibility study in this. So that's the idea in 2009, right? And that's another paper. That's an easier to read paper if you're interested in reading it. But basically, we speculated that the future of main memory will be more persistent, and you will actually use these scalable technologies that are useful. But you can see that there is a huge gap in terms of time frame, right? We were actually envisioning this 2006 or so. And this thing was finally shipped by Intel in 2019. That's 13 years of time frame. So it's good to keep in mind that what we're covering here is very different from software. When you're software, you can write a program and you can execute it right away, right? But when you're designing a computing platform, especially if you want to create a new technology, a new device, it takes a long time. In this case, I think I would even consider things more lucky. It's 13 years. It could be 20 years, 40 years, right? 50 years. That's the interesting part of doing fundamental, working on something as fundamental as computer architecture, basically. You can have an idea, and that idea can be enabled 30 years later. We will see that the original systolic arrays paper, which is really the basis of a lot of machine learning accelerators, was written in 1982 by H.C. Kong at CMU, at Carnegie Mellon University, actually. Actually, he developed the idea earlier in the late 1970s. Systolic arrays were always very interesting, but they never took off until the machine learning application came in 2000, at least it became popular in 2012 and 2013. And when people figured out that machine learning is a very good fit for executing on these systolic architectures, now you see that systolic architecture idea, almost 40 years later, having a lot of impact in terms of the design, in terms of the computers that we use. So you will have systolic arrays. If you recently bought a phone, you probably have a systolic array executing your machine learning applications, maybe spying on you, tracking what you do, who knows? It could be used for a good purpose and bad purpose. Always remember that, it's technology. But it's doing something, and it's using the fundamental principles that we will cover in this course. Okay, so I think this is a good place to take a break, because I'm going to skip to some other examples. So let's take a break. I'm going to give you a 10-minute break today. Let's take a break until 2:12, and then we'll continue. Does that sound good? Okay, 2:12, 10 minutes and counting. Okay, everyone, it's time to start. So we're starting actually a bit late, which means that I'm not a predictable system at the moment, because we were supposed to start at 14:12 and it's 14:14 now. We're 2 minutes late. But at least it's not early, so you don't miss the, miss the tram, right? So that's good. Okay, so before I move on this one, I mean, we can talk a lot about this memory, actually, because this is, again, as I said, this is something very close to my heart. We've been working on memory for almost 2 decades now, actually. But if you look at this, this is also a much higher capacity than your existing DRAM. So there's a premise here that you can actually accommodate much larger workloads to execute on a cell phone, for example. A lot of these cell phones are limited in terms of what they can execute in terms of memory capacity. So memory capacity is a big limiter. So if you actually replace or augment what you have in memory with this sort of technology, you can get much higher capacity. At the same time, you can get non-volatility, so you can actually manipulate persistent data at a lot more persistent data that you can very quickly. So these are actually, in my opinion, game-changing technologies that can change the way we think about systems into the future. For example, file systems may go away, right? You may actually use simple loads and stores, and you may actually have persistent data structures as opposed to file systems. Think about it. Okay, so let me go into some other thing. This is another interesting thing that's happening in architecture today. Has anyone heard of this chip? This Cerebras wafer scale engine? So this is an engine that was recently introduced. I don't know if it works. They say they fabricated it, but look at the comparison point. This is the largest GPU. GPUs are some of the largest chips that we have today. Actually, they are the largest chips. It has 21 billion transistors, and it's 815 square millimeters, as you can see over here. And this thing is a wafer scale chip. So when you actually manufacture semiconductors, you actually have a wafer. Normally what you do is you cut the wafer into pieces, and each piece becomes a chip. These folks said, we don't want any of that. Why? Because we actually want to execute machine learning workloads and train very large models. We want to get a lot of data in. We want to train this model, and we want to do it accurately. For that, we need a lot of data. We cannot afford going to memory every single time, so we're going to have this huge chip that has a huge amount of on-chip memory that can be accessed relatively fast, and at the same time have a huge number of processing units, as you can see with this number, 400,000 cores on the same chip that can execute this machine learning workload, training workload, very fast. And that was their design point. That was their goal. And you can see that it has 1.2 trillion transistors and 46,000 millimeters square. So it looks like this, basically. You can hold it in your hand. So it's not like this. So clearly, that's a trade-off that these folks made. And this is happening because there's a huge demand for these workloads and training. So of course, this is going to be much more costly compared to this one, right? There are going to be reliability issues, because one reason why you cut a wafer into smaller pieces is because you have a lot of faults in different parts of the wafer. And if you cut into smaller microprocessors, the probability that you're going to get a fault in a piece is going to be lower. But if the entire wafer is going to be your processor, then you will have faults in this one, for sure. And of course, you need to tolerate those faults somehow. So there are clearly a lot of different trade-offs that you make when you go into a design space like this. But people are making these trade-offs to actually accelerate these workloads that demand a lot of performance. Right? And the cost is another issue, right? Somebody needs to pay for this. How do you cool it down is another issue, right? Today, we actually have difficulty cooling down these GPUs because they generate a lot of power. How do you cool this thing down? That generates even more over here. So think about this. But this is an example, and people are actually pushing the boundaries toward this direction. Of course, the jury is out. It still remains to be seen whether this is going to be successful in the long term. This is a startup that has developed this. But if it is successful, it could be a game changer, right? Okay, this is another example. This is also a startup that introduced this particular module in 2019. It's UPMEM. And it's essentially a DRAM module. It's a memory module, but it has processing inside it. So you could actually process the data where it resides, or close to where it resides. So I'm not going to go into the detail of it, but basically, this way you don't need to bring the data into some other processor through energy-hungry, long latency interconnects. You basically bring the data into a processor that's inside the same chip, DRAM chip, and that way you actually reduce the latency, improve the energy efficiency. You don't cause a lot of data movement across the system. So this is very fascinating, I think. And this is actually another paradigm that is going to be very interesting to follow going into the future. Again, this is also something close to my heart because we've been working on processing in memory for a long time. And processing in memory means that you have memory chip. Why don't you actually have the memory chip also do computation? I believe human brain is similar to that, for example. But of course, I don't want to speculate right now. But basically, this is a very interesting paradigm that's being explored right now so that we can actually minimize the data movement, maximize the energy efficiency of the systems that we have. So we will talk about that later on. And we've actually been doing a lot of interesting work showing that there are a lot of benefits in terms of processing in memory. But these are happening right now, actually. Another thing that we discussed is this example from Tesla. These are actually real. I believe they actually employ in their recent cars. If you bought a Tesla, you're probably using these chips without knowing it. So they exist. And these are actually also designed so that you can actually specialize for the application, right? And I already talked about Google TPUs. TPU means tensor processing unit. Essentially, you're doing matrix multiplications. This is the second generation. So initial Google TPU was designed for inference, meaning you have a model that's already trained and you ask questions to it. So the boring questions, you give a lot of images and you decide whether it's a cat or a dog, right? So that's called inference. You already have a model and you basically ask questions to it. But the more recent TPUs were designed to do both training and inference so that they can actually train models so that they can do inference on those models later on. We're going to cover these later on briefly. But keep in mind that these are all based on fundamental architectural principles. Systolic array is one principle that we discussed earlier. And clearly, there's a lot of system-level work that needs to go into it. I want to show this picture because this is really the core of it. It's really this matrix multiplication unit. You can do 64,000 multiplication operations per cycle in a single clock cycle, which is a lot. We're going to see one operation per clock cycle very soon in lectures 5 or 6, but we're going to multiply up as we go forward. And a systolic array enables a large number because you're actually operating many units in parallel. at the same time. But to be able to make use of it, you need to actually design a system that takes the algorithm and actually pushes the algorithm data into this matrix multiplication unit. So it's not just this matrix multiplication, it's not just the hardware, it's really the system itself. How do you actually take the algorithm? How do you do the buffering of the data? How do you set up the data? How do you get the data from somewhere to some other place? How do you get the weights for the machine learning model? And how do you actually make sure that all of the data is orchestrated such that they're at the right place at the right time so that this matrix multiplication happens very quickly? That's the idea. So these are actually full system designs in the end. That's why this expanded view of computer architecture is really important. Today, computer architectures are not just this matrix multiplication unit or the microprocessor itself. It's really how you get the algorithm running on the hardware that's specialized for the algorithm itself. Okay, and there actually, this is, I don't want to be biased. It's not just Google, right? Even though Google is probably one of the first ones to publish this work. And it's always good whenever a company actually publishes what they've done. But there are actually many, many companies that are actually designing these AI ML chips and specialized systems. And this is something that I found in one of the websites recently. I don't know if this is true. I cannot vouch for all of that. But this basically shows that there are a bunch of tech giants or system-level companies that are designing these chips. They're IC vendors, traditional IC vendors. They're the ones who are designing these chips, right? Clearly, you know some of them, Intel, Samsung, NVIDIA. They're known for designing chips. But a lot of the other companies are also designing chips today. And you can see a lot of startups in China, worldwide. And there are also compilers and benchmarks and system infrastructures that need to go with these sort of chips. So you can see that computer architecture is everywhere. It's not Intel or AMD or NVIDIA anymore. It's really across the board. Okay, so let's talk a little bit more. So there are other interesting things here. This was performance and efficiency, but reliability and security are actually becoming bigger and bigger problems today also. Clearly, reliability and security are problems in the Tesla engine and all of the other engines that we've discussed. But there are also other very peculiar issues that are happening today. Some of them are due to the technology scaling, and some of them are due to the algorithms we employ in the designs that we have. Now, let me give you some examples. I'm going to talk more about these hopefully tomorrow, but how many of you heard about Rowhammer? Okay, that's interesting. Some of you heard. Where did you hear about it? Anybody?
Online in news.
Online? Okay, online news, okay. Not in one of my lectures. Okay, because I like talking about it because this is something that we found. So basically, it's this. You have a hammer and you hammer memory and your memory goes bad. This is a good analogy, actually. This is a good analogy. I'll give you the idea. Basically, the idea is if you keep accessing memory, just reading it, sometimes you're able to flip bits, meaning a bit becomes, a bit that used to be 1 becomes 0, because you're able to access memory fast enough. We're going to talk about this more tomorrow. This should not happen. Clearly, whenever you're reading memory, you should not be able to change anything in memory, first of all. But this is happening today because cells are too close to each other. We've scaled the technologies into such small dimensions that whenever you're reading some cell, you're disturbing the other cells around you. And that leads to these bit flips. That becomes a reliability problem. But that also becomes a security problem at this point, because if you're able to flip the right bits, you can gain complete control of some other system. And we will talk about this more. Basically, this is actually, you can predictably induce these bit flips that I just mentioned in commodity DRAM chips. And DRAM is employed in all devices that are general purpose today. So this has DRAM, this has DRAM. This is main memory, basically. And when we actually did the studies between 2012 and 2014, we found out that more than 80% of the tested DRAM chips are actually vulnerable to this. And this is actually interesting because it's a reliability problem, clearly. But it's a simple hardware failure mechanism that creates a widespread system security vulnerability, because somebody malicious can actually exploit these bit flips. They can create these bit flips at the right points in memory such that they can change the permissions to access your memory. And once you're able to flip a bit, that actually encodes your permission to do privileged stuff on the system, then you can actually gain access to the system. So if you probably don't know about virtual your page tables and permissions. We will talk about that actually toward the very end of this course. So you will appreciate this a little bit more when we actually are in lecture 24 or 23 or 22. You will see that. But basically, you can change the permissions in your system by flipping the bits. So you should not be able to do that in systems. And actually, if you're interested, you can read articles that look like this. People are writing articles that say, forget software, now hackers are exploiting physics. And this is really about physics in the end, because you're really accessing some location, and the fact that you're accessing this location is affecting some other location that you should really not have, you don't even have permissions to touch. Okay, some famous hacker on the internet, after this row hammer was exposed, they actually tweeted this thing. It says, it's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door that you were after. Now, you will understand this more, perhaps. Let me give you a little bit more insight into this. Basically, if you look at memory, and we will see this in more detail later on, a memory consists of rows of cells, and you usually access a row. Whenever you want to access data, you access a row. Accessing a row means you activate that row, meaning you apply high voltage to that row. And that high voltage, you apply high voltage to that row. And when you want to access some other row, you basically apply low voltage to that row, meaning you pre-charge that row. Now, if you keep doing this repeatedly, accessing means if you want to access a row many times, you keep doing this repeatedly. You activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge, activate, pre-charge. And if you do this enough times, it turns out because some of these cells are vulnerable and they're too close to these cells that you're hammering, let's say, they flip from 1 to 0, 0 to 1. It doesn't matter. You can read the papers as to why it flips from 0 to 1 or 1 to 0. But the important thing is some bits flip. And they're not supposed to, clearly, right? So when we actually discovered this, we call this a hammered row, and we call these the victim rows. And for a reliable memory, this should not happen, but it's clearly happening. And we show that in most DRAM chips you can buy today, you see these problems. And what is most? Most means more than 80%. When we tested in 2012 to 2014 timeframe, more than 80% of the chips were vulnerable. And we wrote this paper that talks about this, and later people actually built attacks, many attacks that actually take advantage of the fact that you could do this row hammer. So, for example, some folks show that you could actually create an app that runs on an Android phone, and this app discovers which part of your memory is vulnerable to these attacks, and it's not that hard to find that because a lot of your memory could be vulnerable, and it basically fools your operating system to allocate pages to those vulnerable locations such that this malicious app can actually take over your phone. Meaning that take over your phone, it basically gets supervisor privileges on your phone, which means that it can have all access to your data, and it could block you access to your phone also. Right? So that's the idea. So this sort of bit flip, it may look harmless, let's say, but it actually enables a security problem also. And we will see this more in the next lecture. And later, actually, we were invited to write this paper that talks about what has happened in terms of row hammer in the last 5 years. And we also talk about what will happen beyond. And this problem is getting worse. So the reason this problem exists is things are just too close to each other. We're cramming more components into the same area. And we want to cram more components into the same area because that gives us higher capacity. But it comes with these side effects that are not good for reliability. And whenever you have these reliability issues, that also causes security problems. And this could also be a safety problem, right? If you're to have a self-driving car, and if someone is hammering you this way, you may not be able to self-drive anymore, right? Not in a good way. Okay. Has anybody heard of these? Meltdown and Spectre? Okay. Okay, before we go on, maybe you have a question. Yes?
Did something get done about these problems, or are we still well?
Yes, so something has been done. We'll talk about some of that tomorrow. Manufacturers are clearly now aware, and they're actually putting solutions. But it's not clear if all of those solutions are good enough to prevent all the attacks. So it's because the problem is getting worse into the future also. Okay, so more people heard about these, right? Clearly these were publicized a lot recently. So these are another example of the security problems that are happening today. These were discovered in 2018, 2017, 18 timeframe. And these are attacks that many general purpose chips are vulnerable to, not because of technology reasons, just we discussed. Row hammer is there because we're cramming more components on a single memory device, right? Here, we're employing mechanisms in our chips. Actually, a lot of the mechanisms we're going to see in this course. I believe you're going to see all of the mechanisms in this course, actually. Here, you may not be able to understand Meltdown and Spectre perfectly because there is a lot that is involved in there. But basically, they enable someone to steal secret data from the system, even though essentially they have no privileges. Your program and data are perfectly correct. Rovhammer, that's not true, right? You basically create some incorrect data to exploit the system. Here, your program and data may be perfectly correct. Your hardware behaves according to the specification, and there are no software vulnerabilities or bugs. So why does this happen? Because modern processors employ many different mechanisms, and one mechanism they employ, which we will also see later on, is speculative execution. Basically, they execute things that they're not supposed to execute. Why do they do that? Because they don't know what to execute next. So if you're taking a branch, for example, if you have an if, then else statement, the processor actually processes instructions early in a pipeline manner, as we will see. So when you get to the branch, you don't know which instruction you should execute next in the processor. So the processor takes a guess. It says, I'm going to go this path. And if that path happens to be wrong, you execute a bunch of wrong stuff that you're not supposed to execute. Now, the processor does the correct thing, meaning it recovers. So all of these results never become visible to the software or the system, but they may actually leave traces of the secret data that they have fetched in the internal storage. That's not directly visible to the software. But someone malicious can actually access that data. So basically, speculative execution brings data that's not supposed to be brought or accessed if there was no speculative execution. And a malicious program can inspect the contents of this internal storage, cache, and we will cover caches also, to infer that secret data that it's not supposed to access. It can still not access it, but by doing stuff to the cache, by probing the cache in particular ways, and by constructing the attack in particular ways, it can infer whether the data that's stored over there, whether each bit that's stored over there is a 1 or a 0. This is called leakage, side channel leakage. Essentially, you're leaking information because you have some side channel here. And a malicious program can actually force another program to speculatively execute code that leaves traces of secret data. So it could actually construct this attack and make it more effective by forcing some other program to go into the wrong path and execute speculatively. Okay, you may not understand any of this at this point, and it's actually a relatively complicated attack. Rovhammer is a relatively easy attack. You basically hammer, you get a bit flip, and you just need to exploit that bit flip. Here, you actually need to do a lot of hoops to actually exploit it, which is also very, very interesting. And this happens because people have been designing processors from the performance perspective. Basically, you want the highest performance, so all of these mechanisms, speculative execution, caches, they're all added into the processor so that you can actually improve performance. People have not thought about the security implications of this, because that was not the design mindset for decades and decades. Today, we're in a very different design mindset. Security is becoming one of the core focuses of design. And because of these reasons, we should actually pay more attention to security. But the reason this happened is because of the design principles were never thought in the general purpose domain in terms of security. In fact, it was actually performance and cost initially. Cost may be secondary sometimes, but performance is really important. In the late 1990s, early 2000s, it became energy and power also. Now energy and power are really important, of course. It's not just performance and cost, it's performance, cost, and energy and power. Now, reliability and security are actually becoming very, very important design constraints in the picture. So remember, I talked about design constraints, design goals, right? You always have an ordering of these. Sometimes security may be a bigger ordering, may have a higher order of importance compared to performance. Not always, of course, right? The question is, how do you achieve a good balance between them, especially in the general purpose domain? Okay, so if you're interested, you can actually read a lot of papers related to this. This is actually the first time it was exposed by multiple people, but Jan Horn from Google Project Zero actually did a lot of work on this one. And it'd be really, you might want to read this. So it says, reading privileged memory with a side channel, which is a nice name. Okay, so that was reliability and security. So let's talk about more demanding workloads, even though I've been talking about them more or less as we go along. So today, actually, we have many more demanding workloads than we had in the past. Workloads are becoming much more demanding. Machine learning is a very good example of this, but it's not just machine learning. Let me give you one example of this. This is also something close to my heart. We've been working on bioinformatics for some time. And these devices, has anyone seen these devices? These are nanopore sequencing devices. No one? Okay, good. Okay, there's one person. I was going to say I put up something that no one here has seen, which is not an easy probability, right? Because we're talking about 500 of you. And There's at least one who has seen this. That's good. So this is a nanopore sequencing device. And this was actually, so you can see the size of this, right? You can actually buy this for $1,000 or $2,000, and you can actually do the sequencing relatively easily compared to using a huge machine that's extremely expensive to do the genome sequencing. And this actually, I believe, actually revolutionized how we do the sequencing. And the technology that goes into it is very interesting because it was a revolution in terms of the technology itself, because it enabled very fast sequencing at these dimensions of genomes. Anyway, I'm not going to go into more detail, but you can see that this device now you can actually sequence a lot of genomes relatively easily, relatively cheaply. And people are actually using these devices to sequence different viruses, for example, Ebola, whatever you can think of, right? And this is generating a lot of data. And this is actually a very interesting workload. Can we actually take a device like this and create a platform that can actually do the genome sequencing in real time? Real time meaning, can you ask a question to this device, and the device can tell you the answer? For example, what is my vulnerability to this particular drug? Or what is the genetic similarity between this virus that I don't know and this virus that I know, right? Or these 1 million viruses that I know. Where does this virus sit compared to those, right? You can actually ask those questions, and these are very computationally demanding questions, but they can be enabled by this sort of technology, and this is an application that can be enabled. So you may not be, so basically this can generate a lot of data, but that data, actually the analysis of that data leads to a big performance and energy bottleneck. So this is one example workload. And actually, if you're not convinced, these are actually being used in real life. You've probably heard of coronavirus, as we discussed earlier. But these actually devices are being used to understand the coronavirus today. And I hope these devices are useful because these are much faster, much easier to do massive scale testing of the viruses compared to those much larger devices that are older technology. Okay, anyway, you can read more articles on this one. Okay, but basically, it turns out this is a bigger device, and bigger device has similar problems, although smaller devices can generate a lot more data faster. Basically, you need to take this data and you need to understand it, and you need to understand even more, and then that leads to scientific discovery or medical benefits, right? But in the end, we're really bottlenecked by how fast we can process this, how efficiently we can process it. So this large amounts of data that's generated by the new workloads that we have leads to performance and energy bottlenecks that we didn't see before. That's why computer architectures are becoming a lot more important today, because we can generate a lot more data than we can compared to even 5 years ago. And I don't even want to think about 20 years ago, right? 20 years ago, we were not generating a lot of data. Going forward, we're going to generate a lot more data. Okay, there are other examples of this. It's not just genomics, but you can see that there are a lot of workloads, like social networks use a lot of graph processing, but bioinformatics also uses graph processing. A lot of machine learning algorithms use graph processing. But there are a lot of other workloads that can actually work on a lot of data, and data usually is a performance energy bottleneck. Even in the, I don't want to call this the lower end, because some of the highest performance processors go into this, because they need to be also energy efficient at the same time. Even in this domain, you have a lot of workloads that generate a lot of data, or you actually manipulate a lot of data. Clearly, machine learning is one example of this also. And again, data becomes a performance energy bottleneck over here. And we're going to talk about this, and keep this in mind when we talk in the lectures. We're going to start from the fundamentals, but whenever we're going to talk about the fundamentals, we're going to start with a von Neumann machine, where you have an instruction, and it manipulates data, and you need to move the data from the processor into the, from memory into the processor. So that data movement actually leads to a lot of energy in systems today. And we actually recently did this study together with Google. This took us about 1.5 years to really analyze the workloads that they have. And we found out that on these workloads that I showed you in the previous picture, the browser, the machine learning framework, video, playback, and capture, more than 60% of the entire system energy is spent just on data movement, just moving data from the processor to memory. So it's good to keep this in mind while you're actually listening to these lectures. That's one of the reasons why we actually are designing different paradigms today, or looking into different paradigms that can actually minimize that data movement. Okay, so what else? I can go on, but I'll try to summarize. Basically, there are many novel concepts that are being investigated today in computer architecture some of which we're going to touch on, some of which we're not going to touch on in this lecture. Basically, we've already talked about processing in memory near data, neuromorphic computing, that's also very interesting, more similar to how the brain operates. Fundamentally secure and dependable computers, how do we design them? I think of this as rethinking the full stack. Can we actually rethink how we design the computers today, as opposed to doing the same thing that we've been doing for a long time? New accelerators are popping up, as we've discussed, and I think of these as algorithm hardware co-designs. And these are accelerators for artificial intelligence, machine learning, graph analytics, genome analysis. You can keep adding your favorite applications over here. Of course, if your application has a lot more data, you get a lot more benefit. And we also have new memories and storage systems that I discussed earlier, non-volatile main memory and perhaps more intelligent memory that can do some processing close to data. So my point is, computing landscape today is actually very different from 10 to 20 years ago. When I was studying computer architecture, I was very fascinated with it. I mean, I took my first class in 1998 from Yale Pat, who became my PhD advisor later on, and I was always fascinated with computer architecture. But at that time, if you were studying computer architecture, you could easily find it boring, in the sense that Intel was really the dominant company, and general purpose computing paradigm was really the paradigm of how you design and build computers. Basically, a lot of the principles that we're going to talk about were the principles that were not questioned. Even GPUs were not there at that time, actually. I mean, GPUs were there, but they were not really popular at that time. But today, because we have different applications and also technological problems, they demand novel architectures. That's why we're seeing these proliferation of architectures. It's not just it's not a very sophisticated general purpose engine anymore. In fact, most of the system is consisting of accelerators today. Maybe general purpose engine is handling some of the workload, but it's going to become more and more heterogeneous going into the future. So at this point, basically every component and its interfaces, as well as entire system designs, are being re-examined today. And that's why we have a picture that looks very heterogeneous like this. And again, as I said, we're going to cover some of these. So I think hopefully one of the takeaways from this course, maybe you will not realize at the end of the semester, but maybe hopefully you'll realize at some point in your lives, is that you can actually revolutionize the way computers are built if you actually understand both the hardware and the software. Because it's not just hardware, it's not just software. It's really hardware, software, and system co-design today. And if you can change each accordingly, you can actually get to a much better place. Basically, you can invent new paradigms for computation, communication, and storage. We will see some of them, but we will mostly cover the basics this time. And I think I will recommend this book to those who are interested. Has anyone read this book? It's Thomas Kuhn, The Structure of Scientific Revolutions. Somewhat. Somebody half raised their hand, I think. This is a book that I would really recommend. It's not an easy read. It's a bit tough read, but basically, Thomas Kuhn this is a philosophy of science book. Basically, Thomas Kuhn is a very famous philosophy of science professor, and he basically analyzed a lot of scientific revolutions in physics, chemistry, astronomy, and he basically looked at how these different ideas come about. And usually what happens is there's normal science, meaning you have a normal way of dominant paradigm that explains things, that the way you design things. So you have a dominant theory that's used to explain things. It's business as usual. Everything else is considered exceptions. Dominant theory dominates. Exceptions, okay, they're an exception, right? So from the computer architecture perspective, you have a general purpose processor. Okay, somebody provides a GPU. Okay, that's an exception. That's not an important workload that you're accelerating. But over time, what happens is this dominant theory is not able to explain things very well, meaning this general purpose processor is not able to execute everything that you care about very well. Over time, you come up with much more demanding workloads, let's say machine learning, and this general purpose processor is extremely inefficient. So what happens is the exceptions start growing. Now exceptions become the dominant part, and the dominant theory becomes not so dominant anymore because it cannot really execute these workloads or explain things. So I'm mixing science and computer architecture right now, as you can see. So at some point, there is no consensus in the field, meaning that you don't have a dominant theory, dominant way of designing things. And today, I think we're actually there. We don't have any consensus in computer architecture. We don't have a single dominant way of designing things. Keep this in mind as you go through these lectures. basically we're really re-examining a lot of the underlying assumptions. That's why we're actually having this proliferation in terms of these different types of platforms that can execute different workloads very efficiently. So it's not clear if we will ever reach a consensus. Maybe the consensus will be, oh, we will have very extreme heterogeneity, in the sense that we're going to specialize for each important workload as much as possible, and the general purpose processor will execute everything else that we don't specialize for. And that could be your dominant theory at some point, right? But we're not there yet, I think. We're still re-examining a lot of things in computer architecture. So you're actually studying computer architecture at a time that's extremely exciting, because people are actually experimenting with a lot of these different things, like the Wake for Scale engine or the AI accelerators that I showed you earlier. Okay, and that's Thomas Kuhn, if you want to see what it looks like. And these are the books, basically. I think there's this, what is this? This is the 30th anniversary or 50th anniversary edition. I have a not so good resolution over here. Okay, I'd recommend reading it. So let me conclude this part, and then I'm going to take some time for some other part. But basically, the takeaway so far, and hopefully I've convinced you that this is really an exciting time to be understanding and designing computing architectures. We have many challenging and exciting problems in platform design that no one has really tackled or thought about before. And Rowhammer is one example. No one really tackled or thought about before 2012. Meltdown and Spectre is another example, right? These AI accelerators, no one has really tackled it before, again, 2012 or so, right? And these can have a huge impact on the world's future, because we're going to rely a lot more on the computing devices that we actually built. And again, we're actually going to bet our lives on it if people are actually thinking about going toward that direction. I know that some people are thinking about going toward that direction. If we want to actually bet our lives on it, we'd better be very, very careful. And we should really know how the fundamentals work and how actually we can design good systems. Right? And I think clearly we know the reasons for it. As humans, we always have a huge hunger for things. But data is something that we're hungry for. New applications that enable many, many good things, as well as many, many bad things. But we're hungry for that. And even ever greater realism, we're hungry for that also. Basically, today we can easily collect more data than we can understand and analyze. And this is part of the driving factor. These are the applications, the high level. But the low level is also the driving factor. Basically, we are also, these challenging and exciting problems in platform design are also driven by significant difficulties that we're facing at the technology layers. Again, we want to keep up with these applications, but and to be able to keep up with the application, you need to push the boundaries of the technology. And when you push the boundaries of the technology breaks, meaning it becomes less reliable, somehow energy becomes an issue, maybe it becomes more costly, and we need to somehow handle these things. And I think of 5 different things that happen when you actually push the technology a lot. Energy becomes a problem, reliability becomes a problem, complexity becomes a problem. Actually, a lot of the systems that we're designing are very, very complex systems, and security, as we discussed, becomes a problem, and how do you scale the system becomes a problem also. So we're going to tackle some of these. Keep this in mind again while we're going through these lectures. Okay, any questions so far? Okay, maybe I'll start with some puzzles then now. This is going to be a more relaxed part of the lecture. So relax a little bit. So I like this puzzle because I think computer architecture actually resembles quite a bit building architecture also. So let me ask you the question, what is this? Stadelhofen, okay, people know this very well. And that's also Stadelhofen, right? It looks nice, right? Who thinks that this looks nice? Bahnhof Stadelhofen. Who thinks that it doesn't look nice? Okay, there are enough people who think that. It's old technology, yeah, it was designed in 1980s, right? That's probably why. They're actually going to change it, I think. So I will ask you, what do the following have in common with Stadelhofen? This Garda Oriente, Lisbon. Milwaukee Art Museum, you may have been, some of them. Athens Olympic Stadium. Valencia, City of Arts and Sciences. They all look nice. Oh, look at that. Oculus. Does anybody know what they have in common with Bahnhof Stadelhofen? Yes. Same architect. Who is that? Exactly. And he's an ETH alumnus, and he has a PhD in civil engineering. And basically, the train station has several of the features that became signatures of his work. So this was actually his first, I don't want to call it a masterpiece, but his first big assignment, if you will, Stahlhofen. And later, he built a lot of things, many of them train stations, but not only train stations. Basically, straight lines and right angles are rare, as you can see. And you can read more about him clearly, and that's what he looks like. So this is your first computer architecture assignment. Go ahead and find the closest Calatrava building to this classroom. I'm not going to give you hints, but maybe you know, okay? Yes, that's right, exactly. So now you know where it is, so you can go there. You don't even need to find it anymore, but you can go there. And if you really want to challenge, you can find the farthest Calatrava building to this classroom. Do you know that also? That's a tougher one, right? Close is usually easier. Farthest is, okay, where's the boundary? Okay, and I would ask you to appreciate the beauty and out-of-the-box and creative thinking. Even though you may think Stahlhofen is not that great, think about the perspective of when it was designed. So you're evaluating the design in 2020, but the design was done in 1983, right? Keep that in mind. And think about the trade-offs in the design, strengths, weaknesses, and goals of the design, because this is actually what we do as computer architects also. We have, in the end, you have this platform that is designed, and their strengths and weaknesses and the goals. And you can derive principles on your own for good design innovation. And you can do this anytime during this course. Later during the course is better. You don't need to send it to me. You can enjoy it yourself. But feel free to send it to me also. People have sent it to me in the past. And you can apply what you've learned in this course, think out of the box. And I think these folks who have Calatrava in this case, he has thought out of the box to design these things. He has designed something different, but it's still a principled design in the end. But first, there's an assignment that we're going to do right now. Of course, I'm not going to do it literally. So let's take a look at this one, again, Stahlhofen, and compare this to that. Do you like this one better? Now that's a loaded question, right? Better. Again, you're evaluating design A and design B. And there are different trade-offs that people have made in this design. Clearly, this is more expensive, and Calatrava is not known for his cheapness in terms of his buildings. This is probably cheaper, but this is probably more artistic, better from that perspective, and this is your vanilla train station, right? Maybe it's boring. You could consider it boring, right? So clearly, there are many, many things over here that you can compare. And whenever you're comparing computing architecture, you do essentially the same thing. Basically, there are many trade-offs between the two designs, and you can list them after you complete the first assignment or whenever you want to. And this is some dimensions where you could compare these different designs. These are the evaluation criteria. And that's actually true for computing architectures also, right? A lot of these things over here apply to computing platforms as well, and more things potentially, right? Right now, I'm looking at building architecture or train station architecture. Functionality, does it meet the specification? That's always important, as we discussed at the beginning. Reliability, space requirement, cost, expandability, comfort level, happiness, aesthetics, security, safety. You can keep adding all this stuff. So how to evaluate goodness of design is always a critical question, actually. And this leads to performance evaluation and metrics, and we will see this in this course. Of course, performance, again, is a loaded term. Performance, in computing, performance has been thought of as how fast you can execute a program, but over time, there are many, many different aspects of performance. Energy became a part of performance, so people actually started evaluating designs in terms of performance per watt, for example. How many watts do you spend to do a given amount of work? That becomes your metric, right? And you can actually come up with many different metrics. So reliability, security, keep adding those. Some of these are hard to quantify also. Security, for example, today we're lacking a lot of good metrics in security, for example. Okay, so I'll ask another key question, basically. How was Calatrava able to design, especially his key buildings? Since we don't have a lot of time, I'm going to give you some of the guesses. Clearly, he was a hard worker. He persevered. He was dedicated. Over time, he developed experience. He was creative, out of the box. He understood the past designs well. He had very good, in my opinion, good judgment and intuition. Although some people will disagree with that because his buildings came at very high costs, right? And I'll show you some examples. And whenever I present this in some places, some people are actually bitter because they have a Calatrava building or design in their place, and they were not very happy with it. But it's not the general case. You know, again, that's true for computing architectures also. You have an architecture. It's not perfect science. This also shows that it's partly art in the end. Okay, strong skill combination. He has actually studied math, architecture, art, and engineering. Combination of that. Funding, that's important. Luck, initiative, okay, and we basically can keep going and going over these. And I believe you will be exposed to and hopefully develop and enhance many of these skills in this course. I cannot guarantee all of them, but if you take this course with the right perspective, I believe you will be able to get a lot of these. Okay, let's talk about principle design, because that's really important, and we're going to cover a lot of principles in this course, and strong understanding of and commitment to fundamentals, because I think these are actually distinguishing characteristics of very good architectures in the end. So this is Calatrava in his own words. To me, there are two overriding principles to be found in nature which are most appropriate for building. So there's a principle here saying that we are using natural principles, right? One is the optimal use of material. The other, the capacity of organisms to change shape, to grow, and to move. And other people on his own work, Calatrava's constructions are inspired by natural forms like plants, bird wings, and the human body. And these are examples. This is actually the blueprint. These are some humanoid things, right, as you can see. And his principal design is zoomorphic architecture. I'm not going to go into the details of this. Okay, so this is, so what does this remind you of? This is Oculus in New York City. Actually, this is, you can do this assignment also, go there. And in the past, people who have taken this course sent me pictures from Oculus, and they were happy to be there. I'd recommend going there. It's actually a fascinating building. What does it look like? A bird? Yes? A meat-eating plant. Okay, there you go. You're creative. If you ask Calatrava, he said that the Oculus resembles a bird being released from a child's hand. But of course, you can have different interpretations, clearly, right? It could be a meat-eating plant, actually. That's a good one. But any architectural work, any design has some goal, and maybe his goal was this, but it also has some strengths. And clearly, I'm going to show you examples from criticism that he got, and this is some positive criticism, basically. People appreciate the strengths. Basically, somebody from New York Times, I think, I don't remember who wrote this, but it's a pleasure to report for once that public officials are not overstating the case when they describe a design as breathtaking. There's some journalist writing about Calatrava's building. But you always have design constraints whenever you design a building or architecture. Basically, Calatrava's design was not immune to that also. You can see that in the name of security, Santiago Calatrava's bird has grown a beak. Essentially, its ribs have doubled in number. This is a clear criticism, right? You can see that. Its wings have lost their interstices of glass, blah, 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 blah. It may now evoke a slender stegosaurus that more than it does a bird. So you will get this sort of criticism whenever you design computing platforms also. And if you're curious what a stegosaurus is, it looks like this, basically. And I think you could argue that Oculus looks like a stegosaurus as well. Okay, so no one is immune to design constraints. Basically, even if you have a large amount of money, you're always immune to design constraints. So you can see that security is one design constraint that's very important. And you can see that the design was further modified in 2008 to eliminate the opening and closing roof mechanism because of budget and space constraints. And in the end, the transportation hub, this is a transportation hub actually underneath, it's a massive transportation hub, has been dubbed the world's most expensive transportation hub. It's about $4 billion. And New Yorkers were not very happy with this price. But if you actually go there, you will enjoy it. Basically, you paid a lot of this money to transition to the new technology. And over time, new technology can overcome its costs. Keep this in mind. We're going to pick it up from here. Okay.